Hello there, it's Alana, and I'm back to help with another statistics homework question. This time we're going to do 9.1, number 47 from the study plan. So when you look up here in the corner. All right, so let me click on View an Example and kind of expand it. It says, by how many times does the sample size have to be increased to decrease the margin of error by a factor of 1/10? Okay, cool. So I don't really quite like this explanation. I mean, it's all right, but I think it's a little bit hard for students to understand. So let me remind you of a couple things. We have this formula here, right here, for sample size. See it? Okay, so let me type it up. Bring up a new sheet. So n was equal to 0.25 times z. Oops, z. There we go. Alpha over 2, and then all of that was divided by the margin of error, and then it was squared. Okay? Okay. So what's happening is, and keep in mind, this wasn't the only formula to use. There was the one that has 0.25. Hold on. There it is. So you could use, I'm using the one for 0.25 because I don't know what my prior estimate for p hat is, but if you had a prior estimate, you could use the p hat one. It doesn't really make any difference because it's not going to affect the problem we're doing. I just figured I'd go with the one without p hat since I don't know what p hat is in the first place. Now, my z, remember, is tied to my confidence level. So this guy right here, the z part, is based on your confidence. The more confident you are, the larger the number it is, right? So I'm going to pretend, just for the sake of this, I'm not going to do it in a formal way. I'm going to do this kind of in a trial and error way. So let's pretend we have a 95% confidence level. Oopsie, confidence, I can spell level. Okay, what would that mean? That would mean that z, alpha over 2 would be 1.96, right? No troubles there. We've already learned that back in the notes, how to do that using norm inverse, inverse norm if you're using a calculator, norm inverse if you're using Excel, and also StatCrunch does it as well. It's right here, 1.96. It's the one we use the most often. Okay, cool. All right, so you'd say, okay, if I got 95% confidence, it's cool. That's what's going to be there. And then what's going to happen is, let's pretend we have a margin of error of, let's say, 3%. Now I'm using percentages here because this is for proportions, remember, that we're working with. So that would mean we're working with small decimals. Nothing ever is going to be bigger than 1. So we have margins of errors of 3%. Okay. So what's going to happen here is that n would be equal to 1.96. Oopsie, 1.96 over 3%, which is 0.03. And then I'm just going to grab Excel real quick and make it calculate this for me. So equals 0.25 times 1.96 divided by 0.03 squared. Actually, you know what? If I was smart, I would say z, let's see, if I make this 95% confidence, right? So I'm going to make, this is 0.95. And then I'm just going to be smart about this and say, this is my, oops, here, confidence, 0.95. I'm going to prove something to you guys here. And that would mean my z, remember, is equal to inv norm, or is it norm inverse? There it is, norm inverse. We want the S inverse because it's the standard normal curve. And my probability is, well, it's alpha over 2 or 1 minus alpha over 2. So it's 1 minus 0.05 divided by 2. Oh, 0.05. Hold on, I won't use it that way. It'll be, hold on. Let me back up. What's alpha? Alpha is 1 minus this guy right here. Okay, so alpha over 2 would be that value divided by 2. I'm doing this so that way I can fiddle around with any of these values I want and other things will change automatically. So the z alpha over 2 would be equal to norm.s.inverse Now the new system has the S one for standard normal. The old one didn't used to have that. So if you're working off the old function, you'll have to say 0 and 1 for your mean. Here it'll be norm inverse, and then it'd be the probability would be, technically it's 1 minus 0.025 comma 0 comma 1 if you're working off the old system. The new system you can just say norm dot s dot inverse I on v, and then the probability is 1 minus 0.025. Right, again, you're trying to do the positive one, the one on the right. If you remember back to the picture, hold on, right back here, right, there's one on the right and there's one on the left. So what I'm doing is I'm making it find the area in the whole tail. So like if this is 0.025 over here, then this middle part's 95, and then this tail over here is 0.025. So I'm making it find the center white portion and this yellow or this red portion over here on the left together. Okay. All right, so hold on, let me get back here. Okay, so there's my alpha. So then my n, oh, let me put in my error just for fun. Error would be 0.03, say. Okay, so then n is equal to 0.25 times, and then it's this value, 1.96, divided by this error right here, squared. Oops, squared. Not times 2, to the 2. Oh, yes, fine. That is not where I meant for that to go at all. Close parentheses. There we go. Beautiful. All right, and then we want to round up. Equals that number, oopsie, round up. Yes, that's an actual function in Excel. And I'll round up that number to 0 digits, because you can't pull 0.07 of a person. Okay? All right, so this is the formula for n. Cool. All right, so you're thinking, why did you do all that work? Well, because I wanted to prove something to you. So let me show you what's going to happen if I change it. So let's suppose I leave it at 95% confidence level. But instead of having an error of 0.03, what they're asking about here in this problem is, what if you change it by a tenth, right? What if you change your margin of error by a factor of 1 over 10? What's going to happen? All right, so instead of 0.03, what I want is 0.03 times 1/10. So 0.003. Look what happened, right? Instead of 1067, I get 106707. So look at what happens to the decimal place. Instead of the decimal place being, oopsie, between the 7 and the 0, it's over here between the 7 and the 2. How many spots did it move? Well, you could figure that out really easily. You could just take this 106707 divided by this guy, and you're going to get 100. 100. Interesting. Where did that come from? Was that just, crazy? No. Okay, so what's happening is, right, oops, and we found this to be 1067.072, just so we know for later. And then you would round it, okay? All right, so when we decrease by 1/10, right, decrease the error by 1/10, what happened? Well, in here, it becomes 0.003, right? Squared, right? But what that meant is that this decimal place moved to here, okay? And so then we can make a ratio of 106707.2 divided by 1067.072, and we got 100. All right. Oops, and that was the answer that they were looking for right there. Now, it's not a formula way of doing it. It's more just trying stuff out and seeing what happens. Now, there is a formula way to do it. Let me see if I can show it to you. So let me take this formula. And let me suppose that instead of using error, I use error times 1/10, right? Because that's what they're actually asking us to do, right? Take a tenth of your error. Okay, well, let me just write this out. So this is equal to, okay, so I've got this, you got to remember something about math, which is that you can take the top number and square it. In other words, I'm distributing my squaring. And then I can take this number and square it. And And then I can take my error and square it. Okay. It's a rule from back in an algebra class somewhere, basically, that says, here, I'll write down the rule. If you have a to the, well, actually, a times b to the n power, that's a to the n power times b to the n power. Oopsie. Right, there we go. All right, so what happens here, right here, is what's interesting to us, because the rest of it's kind of how it's always going to be, right? Over here, we're going to have 1 over 10 squared. Okay, so this is equal to 0.25 times fraction 1 over 100, but in the denominator. So it's 1 over 100, right? That's this fraction part right here. And then I'm going to split off the z part and the e squared part. Matter of fact, you probably don't like that too much. All right, let me break this up separately. So this is 1 over 100 right here. There we go. 1 over 100 right there. Because 1 over 10 squared makes 1 over 100. Okay. Okay, but the z and the e are still squared, so they could just be rewritten just like they were. 0.25, and then you could write, oopsie, come here, parentheses thing. All right, so then you could say, okay, well, that's 1 over 100, and then the rest of it's just still sitting there, right, without the 1/10 part. In other words, I'm taking the 1/10 and I'm squaring it, and then I'm busting it out of there. Right, and the rest of the stuff just sits there. So the z sits there, the e sits there, but the 1 over 100 comes out. But now you got to remember something from math class a long time ago. When you have this part, 1 over 100, that's the same thing as 1 divided by 1 over 100, which is the same thing as 1 times 100 over 1, which is 100. And that's why you're seeing it flip the way that it does. So that's like the algebra way to prove it without any numbers, is to kind of use this formula thing. So you write down the formula but put a 10th in there. Then you break out the 10th, you square it, and then you break it out of there. So it's 1 over 100, but since 1 over 100 is in the denominator, you'll flip it, right? And it'll flip up into the numerator down here because you multiply by the reciprocal, and that gives you 100. Okay, so that's another way to see it. So that's like the more formal way, and that's the way they're trying to show you, formula way. Oh my goodness, I can't type. All right, there we go. So that's like the more formal way to do it. Oh, let me just... So you got to remember that from back in the day. There we go. Right, so that's like the more mathy person, math teachery way to do it, if you will. But it's correct, right? It works. It's just because when you divide by 1/10 squared, you're dividing by 1 over 100. You flip it up, and that makes 100 over 1. Ta-da! But if that's a little hard for you to kind of spot, then it might be easier to think of it this way, like trying some numbers and see what happens. Like say you're going to do 95% with a 3% margin of error, and then change it to decrease the error by 1/10, which make error equal to 0.003, and see what happens, right? All right, and the way I got 0.003 is I just take 0.03 and times it by a 10th. If they ask you to do a half, you do 0.03 times a half. You do whatever they ask and see what happens. And you're really interested in this ratio. How did this old number compare to this new number? So I take the new number and I divide it by the old. So in this case, 106,707 divided by 106.707 to see what happened. And while I'm on the subject, just for the fun of it, let me just show you one other thing. What would happen if you leave the margin of error the same, but you boost your confidence level? Oh, look at that. You need more people. Because to be more confident, if you leave everything else the same, you're going to need more people, more sample size. All right, I hope that helps. I'll see you back here for more videos